Hello everybody! So today in class we did an activity that helped us sort of visualize how optimization problems work. What we're going to do in today's notes is look at some specific examples as well as try to develop a system that we can use or sort of a procedure for solving these problems. Every one of these problems is going to be a little bit different from every other one of these problems. So it's important to have sort of a general strategy for attacking them and being able to work our way through them. Let's start by listing a strategy. Now we did a little bit of this in class today where everyone kind of wrote out what their strategy is. This is my strategy. You don't have to go with this. You can always go with the one that you wrote out in class today if that makes more sense to you. But I did want to share with you how I think through these problems. So the first thing is to develop one or two equations. And you have to decide which one you are trying to optimize. So it's very important to read the problem carefully. Some of these problems will just have one equation and some will have two. If you do have two problems, it's important to know which one you're trying to find the maximum or minimum of. Then you're going to substitute the equations so that you only have one variable. Now this is only if necessary. If your problem already only has one equation with one variable, you don't really have to worry about this. But if you do have two equations and two variables, you need to kind of make this become one equation with one variable, which means substituting. Then you're going to find the maximum or the minimum. Now that sounds really easy, but to do that, it actually involves a process. So in order to find the maximum or the minimum, you need to take the derivative, set it equal to 0, and then solve. That should look familiar. That is something we practiced in Chapter 5, Part 1, where we talked about extreme values and finding maximums and minimums. Then you, at the end, want to make sure you answered all parts of the question. Let's take a look at example 1 and see if we can figure this one out together. So this is an example that requires just one equation. It says here the apartment rental company has 1,600 units available, of which 800 are currently rented at $300 per month. A market survey indicates that each $5 increase in monthly rent will result in 20 new leases. How much rent should be charged to maximize the revenue? So as I read this problem, I'm realizing that the thing that we're going to change is how many increases we're going, or how many decreases we're going to make. So it says that we're going to, if for every $5 decrease in monthly rent, we get 20 new leases. The first thing I'm going to do is write down what X stands for, because at the end of the problem, we're going to need to make sure we answered the question. And so sometimes the answer is not just as simple as finding X. In this problem, X is going to stand for the number of $5 decreases that we're going to make. Then it says that we want to maximize the revenue. If we want to find the maximum of our revenue, we're going to need an equation for the revenue. I usually start problems like this with sort of words of what I want to fill in. To me, revenue is always how much money I make how much I charge times how many times I charge it. So if I'm going to make $20 each time, how many times did I make $20? In this problem, it tells me that right now, so let's just work on the how much money I charge part. Right now, I'm charging $300 per month. But it also tells me that I'm going to have a $5 decrease, and maybe I'm going to decrease the price $5 one time or two times or three times. X is going to stand for how many times that happens. So how much I charge can be represented by writing 300, which is my current amount, minus 5 times X. So I'm going to subtract $5 every time I do a decrease. Now, how many times I charge that has to do with how many of these places I'm renting out. It tells me that right now 800 are currently rented, but every time I decrease the charge, I'm going to get 20 new rentals. So I'm going to add more rentals. So how many times I'm going to charge it is going to be 800 plus 20 new ones every time I drop the cost. Now that's all part of step 1. And that's probably the most complicated step, is to develop 1 or 2 equations. I would really, if I was going to try to decide like where do I need to focus my attention and spend my time, that would be the place to spend it. Because if I can't get the equation correct, it's going to make the rest of the problem really challenging. This is all developing an equation. After I developed an equation, if I've got 2 of them, I might need to substitute. In this case, I only have 1. And then the third step, I'm going to find the maximum or the minimum. So the first thing I'm going to do is find R prime. Now, in order to do that, I think it's easier if I have a simplified version of R. So before I find the derivative, I'm going to multiply all of this together. So I'm going to have 240,000 plus 6,000x minus 4,000x minus 100x squared, just multiplying it out, which means I get 240,000 plus 2,000x minus 100x squared. As soon as I have that simplified equation, it makes taking the derivative a little bit easier. The derivative of a number is 0. The derivative of 2,000x is just 2,000 minus 200x. Next, I'm going to make the derivative equal to 0. So I'm going to have negative 200x equals negative 2,000. And then when I divide, I get 10. Now this is all part of step 3 from the steps that we wrote out up above here. This is all part of step 3. We took the derivative, we made it equal to 0, we solved. But the last step is also probably the second most important step after developing the equation, which says make sure you answered all the parts of the question. The question says, how much rent should be charged to maximize the revenue? Now, if X represented how much rent, that would mean that I'm charging $10 per month. But X represents the number of $5 decreases. So what that means is I'm going to decrease the price 10 times. So right now, the price is $300. I'm going to decrease the price 10 times, and I'm going to decrease it by $5 each time. So in the end, I'm going to end up with a monthly price of $250. Let's take a look at a few more examples so we can kind of get an idea of how this system continues to work. The next 2 examples are each going to require us to have 2 equations. So problem number 1 says an open top box is made by cutting congruent squares of side length x from the corners of a 54 by 30 centimeter sheet of paper and bending up the sides. How large should the squares be to make the box hold as much as possible? What is the resulting maximum volume? Now this is very similar to the problem we did in class. We're going to take a sheet of paper, and I do think that drawing a picture here can be very helpful to visualize this. That is 54 centimeters by 30 centimeters. We're going to cut squares from the sides. And we're going to bend them up so that we can get the biggest volume possible. Now, in the problem, it says the side length of the squares should be x. We also used x in class. It says how large should the squares be to make the box hold as much as possible? What is the resulting maximum volume? So if I want to maximize the volume, I'm going to go ahead and write a formula for volume. So the volume of a box is length times width times height. But we're going to need to use a different setup because we've got 3 variables here and we want to only have 1 variable. After I cut out these squares, the length of the box will be 54 minus 2x because I'm going to take an x out from here and from here. The width of this box will be 30 minus 2x, and the height, when I bend up those squares, will be x. I'm going to go ahead and multiply this out to get a simpler formula. So 54 times 30 would be 1620 minus 54 times 2 is 108x minus 60x plus 4x squared. And this is all times x. If I simplify that again, I get 1620x minus 168x squared plus 4x cubed. This is all part of step 1, writing an equation. Step 2 is substitute if necessary in order to get just 1 variable, which in this case is not necessary because we only have an x. So we're going to jump straight to step 3, which is take the derivative, make it equal to 0, and find the max or the min. So v prime in this problem will be 1620 minus, 168 times 2 would be 6, carry the 1, 3, carry the 1, so 336x plus 12x squared equals 0. Now what I'd like to do in this problem is show you how you can use your calculator to solve these. So I'm going to go ahead on my calculator, and because this is going to be difficult for me to factor or to really figure out, I'm going to go to y equals, I'm going to type in my equation. I'm going to go to my window and I'm going to adjust my window. Now the reason I'm going to adjust my window is because there's a certain restriction to what x can be. If I want to cut x out from this box, then x has to be bigger than 0, but it also has to be less than 15. Because if I try to cut out a size square that's bigger than 15, it's not going to be possible if my side is only 30 centimeters. To take 15 from this side and 15 from this side, it wouldn't be possible. So my x's have to be between 0 and 15, which means I'm going to change my window to go between 0 and 15. I'm going to go ahead and look at my graph. And it looks like my maximum of my volume is going to be somewhere up there. Okay, wait. I need to change my window again. -10 to 10. There we go. So it looks like my maximum of my volume is going to be here, where my equation equals 0. So to find this 0, because I want to know where my equation equals 0, I'm going to go to second, calculate 0. That 0 is going to be between 0 and 15, and I'm going to get 6.1897, which I'm going to round up to 6.19. Now, let's make sure for step 4 that we actually answered the question. How large should the squares be? What is the resulting maximum volume? Well, it's pretty easy to say how large the squares should be. The squares should be 6.19 centimeters by 6.19 centimeters. The resulting volume is going to require us to take 6.19 and plug it into our volume formula to actually figure out how big that is. So I'm going to go to my home screen and I'm going to do 54 minus 2 times 6.19. And then I'm going to do 30 minus 2 times 6.19. And then I'm going to multiply by 6.19 because that's x. And I'm going to get 4,539.40 centimeters cubed. And now I've answered all parts of my question. Let's go ahead and try one more problem. So this problem is a pretty typical optimization problem. You probably recognize this if you read it carefully because it actually is a problem you guys solved in pre-calculus as well. It says a rancher wants to construct a rectangular corral using 200 feet of fencing. The rancher decides to build it adjacent to a barn. What dimensions should the rancher use to construct the corral so that will enclose the largest possible area? Now, when it says we're building it adjacent to a barn, I think it can be very helpful to sketch a picture here, so I'm going to. It means if the barn is here, then the rectangular corral is going to be here. Now, what that also means is I don't need a fence on this side of my rectangular corral. So if I give my rectangular corral some labels, I usually call horizontal pieces X's and vertical pieces Y's. Now we want to enclose the largest possible area, so we need to write a formula for area. The formula for the area of a rectangle would just be base times height, which in this case would be x times y. But that makes me notice that I have two variables. If I've got an x and I've got a y, that means I'm going to need a second equation in order to substitute and get rid of one of those variables. So another piece of helpful information that's in this question is that we have 200 feet of fencing. 200 feet of fencing is a perimeter. So if I add up x plus 2 of the y's, I know I'm going to get 200. In order to solve this more easily, I'm going to isolate the x instead of the y. I know our first instinct is usually get y by itself because we do that for a lot of things like graphing. But since the x doesn't have a coefficient, it's easier to isolate the x. Then I'm going to substitute that into my area formula, which means instead of x, I'm going to write 200 minus 2 times y times the other y. I'm also going to simplify this just a little bit because I know that it's usually easier to do the next few steps if I have a simpler problem. So step 1 was write 2 equations. Step 2 this time was to substitute, so we only have one variable. The next step is going to be to take the derivative and find the maximum. So the derivative of my area formula would be 200 minus 4y equals 0, which means I have negative 4y equals negative 200, so y must equal 50. However, the last part of my question is to make sure I answered all of the questions. So the question says, what dimensions should the rancher use to construct the corral so it will enclose the largest possible area? Although it's good to know that the y should be 50, that doesn't mean that's all of the dimensions. So what we need to say here is that the side that is parallel to the barn is a certain number, and the sides that are perpendicular to the barn is a certain number. Now the reason I'm saying it like this, and I'm not just saying the dimensions are 50 by whatever, is because it is significant which of these sides is the one here, because there isn't a partner for that side, whereas these two sides are partnered up and they're both the same length. So the sides that are perpendicular to the barn, based on this picture, are the Y values. So I would say 50 feet there. In order to find the X, the side that's parallel, I would take the 50 and plug it into this equation here. 2 minus 2 times 50, which is 100, would just be 100. So the side that's parallel should be 100, and the sides that are perpendicular should be 50 each. Thank you so much for watching today. I really appreciate it. I look forward to working with you guys over the next couple days to practice these problems.